Okay, we're on 1.8 now. Okay, so leaving 1.6, going into 1.8. This subject is on continuity and what it means to be continuous. When is a function continuous? The short answer is, if you can draw it without lifting your pencil, it's continuous, right? That's kind of the short answer. What we're going to get into is to the minutia as to why it's discontinuous. What does it really mean if I tell you the function is discontinuous, or the function is not continuous, or it does not have continuity? If it has continuity, it means it has continuous. And we're going to talk specifically about continuity at a point. Three things. Philosophically, three things must happen for a function to be continuous at a point. There must be a function value. It's got to have a function value. In other words, you put something in, something's got to come out. It has to have a limit. And that's the new idea we've been working on. It's got to have a limit. Okay? And then the third thing is, whatever the y value is for the function value, whatever the function value is, the y value, whatever the limit is, the y value for the limit, they better be the same. Better be the same. Okay? If one of those rules is broken, it's not continuous. And generally speaking in this class, because that's what we're talking about, is you're going to usually find one of the rules is broken. So let's look at the picture. Now, we had one very similar to this when we talked about limits, okay? Because we're kind of leading up to this kind of idea of what's called continuity. So let's look at this picture here, and we'll go over these three rules. Okay, so I'll slide the board over here. Let's slide the board this way. And I want to make sure we can see the map here. Okay, so first rule was we have to have a function value. What is the function value at 1? Well, when I put 1 in, I can see that 4 comes out. Not the limit, the function value. Literally, it's going to be 4. So, now, if it has a number, that means it exists. That's the, hey, it exists. How do we know it exists? It has a function value. Now, what would the limit be as x approaches 1? Well, remember how we do that. We have to check from the left and from the right. So notice that if on this side of 1, I'm pretty close to 2. On this side of 1, I'm pretty close to 4. So on the left side, I'm 2, and this side, I'm, oh, sad face. The limit does not exist. Limit of f of x as x approach is 1, does not exist. It is not continuous at x equals 1. The function is broken, but you can look at it. I mean, just look at it. It's obviously broken. I mean, when you look at it, you can see right away whether it's broken or not, but the philosophical reason that it's broken is the limit does not exist. Now let's compare that to the next one. 2. Let's look at 2. What is f of 2? Crap, there is no f of 2. It's undefined. So right away, we can say at x equals 2, f of x is not continuous. Now, you can go on and look for the limit if you want. We could do that. The limit from the left would be 1, and the limit from the right would be 1. Now, I did this on purpose, so you could probably imagine that, right? Is at 1, the red one, the reason this thing is this function is discontinuous is it broke the second rule. The limit does not exist. And then at 2, the green one, it's because the function doesn't exist. So in this one, there's a function value but no limit, and that's because it's broken. Okay, make sure you get that right. If it's broken, it's because there's no limit. If there's a hole, it's because there's no function value. Make sure you get that, right? Broken, the limits are going different places. The limit doesn't exist. A hole in the function, oh, it's going there, but it never gets there because there's no function value there, okay? If there's a hole in the function, it's because the function doesn't exist. If there's a break in the function, it's because the limit doesn't exist. Now, you can have cases where both of them are all foobarred, right? But that's kind of generally the basic two. That's why I covered those two. These are the most common two. Now, the third one is the most difficult one for students. Third one here. When I look at this one here, notice that when I put 3 in, 4 comes out. So it has a function value. When I put 3 in to the function, 4 comes out. So the y value is 4. And then the limit, if I'm on this side of 3, I'm very close to 2. And on this side of 3, I'm very close to 2. So you can see that they're approaching 2. So it's got a limit as x approaches 3 also. Oh no, 4 isn't 2 though. Where it's heading isn't where it ends up, right? And this is a weird one because it has a function value and it has a limit. Remember on the other ones, this one didn't have a limit and this one didn't have a function value. That's why they're broken. Well, in this case here, what you have is it has a function value and a limit, but 4 doesn't equal 2. But we don't normally write that. We normally say that the limit does not equal the function value. This was, oh no, this was 2 and this was 4. They're not equal. So we'd say f of x is not continuous at x equals 3. Now I do this next one. I'm going to do the last one, 4, because I just want to do one that is continuous. And normally, when you do this type of homework, it's usually trying to find usually the question is when is this function discontinuous? And the reason is because if we can find the points where it's discontinuous, then we can make the assumption that it's continuous everywhere else, right? That, because not to be too philosophical, but if I can define where something is continuous or isn't continuous, if I can tell you exactly where it isn't continuous, then I'm also telling you where it is, aren't I? Right? Almost like I'm defining something by what it's not. Okay. So anyway, so let's check 4 here. Okay. Notice that when I put 4 in, I get 1 out. Okay. F of 4 equals 1. Notice that on both sides of 4, the numbers are getting closer and closer to 1. I know it looks like it's 1.5, but let's just pretend that I meant for it to be at 1. Well, maybe we draw it just because I want to have all integers for this type of question because they are on AP exam. They normally make them integers. There we go. So notice that the limit as x approaches 4 is 1, and those are the same. So then we know that the limit equals the function value. So yay, we finally found one that is continuous at x equals 4. Matter of fact, that would be anywhere else too. The only place this function is broken is 1, 2, and 3. Everywhere else the function makes perfectly good sense, right? Okay, now I'm going to go back to something called a piecewise function. I'm going to go back to something called a piecewise function here. I didn't write it up, I just realized, so I'm going to have to write it up right now. So let's say one function was 3x squared plus 7x plus 1 when x is less than 1. And let's say I want to make it the sine of pi x over 4 when x is less than or equal to 1. This is called a piecewise function. Okay, it's got a top piece, which is a parabola, and a bottom piece. And we want to graph the parabola when it's less than 1, or we're not going to actually graph it. We're just going to do the continuity. The question is, when the parabola meets the sine wave at 1 here, when it transfers over from one function, are they connected? And so what we want to do is if Let me go through the correct way, and then I'll go through kind of the shortcut way to do this, okay? So what would the limit as x approaches one of the top function be? If I put 1 in, I get 3 plus 7 plus 1, which is 11. Okay? Then if I take the limit as x approaches 1 of sine of pi over 4x, and I put 1 in, that's the sine 4. Now you gotta remember your trig, okay? I know it's kind of sucky, but you gotta remember the sine of pi over 4 is 1. Now you can write it as root 2 over 2 or 1 over root 2. I don't care whether you rationalize or leave it unrationalized, it doesn't matter to me. But here's the point. The limit from the left doesn't equal the limit from the right, so it actually does, the limit doesn't exist. Now it has a function value because of the equal sign. The 1 goes in, and this is the function value also. So just be aware, not that it matters in this particular question because we're worried about the limits, but the equal sign goes with the 1, so this would be equal. If that equaled root 2 over 2, then everything would be cool, and the function would be a continuous function at that point. Now, you probably realize there's a really nice shortcut. Just put the frickin' 1 in here and the frickin' 1 in here and see if they're the same or not, right? If they're the same, it's continuous. If they're not, it's not continuous, right? But technically, you're not when you put the 1 in, because technically you're not supposed to put the 1 in. Technically, when you're putting the 1 in, you're really taking limits, okay? Hence the reason I wrote the limit notation, okay? So, well, 11 does not equal root 2 over 2, so it's not continuous. Okay. Now, just for the fun of it, what if we did this? What if we change this to a minus and this to a 5, and we change this to a 2? What if we did that? So what if now I take the limit as x approaches 1 of the 3x squared minus 7x plus 5, and I put the 1 in, 3 minus 7 plus 5 is 1. Limit of sine of pi over 2x, if I put as x approaches 1. Oh, you know what? I kind of was a dingleberry there. This should say from the left, and that should say from the right. I apologize. Left, and this should be from the right. The sine of pi over 2. Oh, that would be 1. What I'm getting at is it's a coin flip. You have to do the work, right? You have to check, okay? So in the green example, it ended up that the top one had a y value of 1, and when x was 1, and the bottom one had a y value of 1. So what we would say then is the function is continuous at 1. This one was not continuous at 1 when I had these two, the original equation back in. Okay, that's what's called continuity, okay? A function is said to be continuous if it has a function value and it has a limit at a point, and those two numbers are the same, okay? That's called continuity at a point. And it's often with piecewise functions or pictures of functions with breaks in them that you have to kind of answer questions about.